Okay, good day. This is AP Calculus. I am Mr. McColley. This is the presentation for section 5.7. Let's get right into it. This is the final section for chapter 5. We are going to do some integrations whose antiderivatives involve inverse trigonometric functions, and there's only 3 of these, so it shouldn't be too bad. And again, this is probably something that I will have on the quiz, but certainly something that you're going to want to review before you take the AP Calc test. We're going to talk about review the method of completing the square to get it into a form so that we can use these inverse trig functions. And then we're going to talk about a table that is in the book for this particular section that is going to become invaluable as you prepare for the AP Calculus test. So again, let's get right to it. So we have some integral forms that involve inverse trigonometric functions. So you can see that if you have something here where if you have the square root of a difference of squares, then you can, and this is a constant and this is some sort of variable expression where this is the derivative of that variable expression, you can replace that with arc sine of u over a plus c. So these are just really, there's no new math for this particular section. These are just different forms, and they are all written in chain rule form. So these really aren't anything new as far as how you go about doing the integral. They're just different forms, and we're going to set them up the same way. So let's jump right in. I am on page 387, and I am looking at number 4, and that integral there that they give us, it's an indefinite integral, and they would like us to do the indefinite integral of 12 over, let's see here, 1 plus 9x squared. Okay, dx. So I go back to here, and I'm trying to find a form that most looks like it. Well, this one's got a square root in it, and this one's got a square root in it. So we're looking at this particular form here. So, just real quick, you don't have to do this every time, but they put a du here, and they go a squared plus u squared is equal to the, let's see here, it is 1 over a times the arc tangent of, excuse me, u over a plus the constant c. So let's look at what we have here. So if I'm looking at this thing, obviously my a squared is equal to 1, so a will equal to 1. And then my u squared is going to be equal, and this is where it's a little bit different than what we've done in the past, where you're going to say your u squared is your 9x squared, and so your u is going to be the square root of that. So that's just going to be 3x. So when I look for my du, I'm looking for only 3 dx. Now, I have 12, and I need it to be 3. So I'm going to move 4 out and put a 3 there. X plus 9x squared dx. And now I have my 3 dx that I can change into du. I have my a squared, I have my u squared, and I can just fill in what I had before. So I've got the 4 that leaves out front. And so my a is 1, so I have 1 over 1 arc tangent of 3x over 1 plus some constant c. So 4 arc tangent 3x plus c, and that's my final answer for that particular one. So again, not a whole lot of different, just matching it up, figuring out the variables that you need to do, plugging it in, and doing the integration. It's pretty straightforward stuff. All right, let's look at this next one. I got all kinds of stuff here. Now, when I look at this one on first glance, I'm thinking that this is just a simple substitution. And so I'm going to say, and kind of show you what I'm trying to do here. So I'm trying to show you how you can go down one route and say, oops, I've made a mistake. Let's try something else. So I'm thinking, well, cosine is the derivative of sine. So maybe I could let u equal 7 plus the cosine squared of x, then du would equal, well, I got the derivative of a constant is 0. And then since this is really equal to, you got to think of that as the quantity cosine x squared, I'm going to have to do the derivative of that. So I got 2, and it's going to have a chain rule now. So 2 cosine x times, to the first, times the derivative of that, which is sine x. Well, I have the sine x, but I don't have this cosine x either. So this isn't going to work. So we just get rid of it. Try something different. Well, let's look at it in the context of, let's look at it at the context of what we just did. Context of this. Well, if I think of it this way, and I say let a squared be equal to 7, then a would just be the square root of 7. And if I let cosine, or excuse me, let's do it the same way I did the last time. If I let u equal, or u squared equal cosine squared x, then u would just be cosine x, and the derivative of cosine x is sine x. And look, now I have that expression there. So now I can use that exact same rule that we used here, where I have my du, and then a squared plus u squared equals 1 over a times the arctangent of u over a plus c. And now I can just do that exact same thing and say that this is going to be equal to 1 over the square root of 7, that's what a is, times the arctangent of u over a, which in this case was cosine x over 7 plus, oops, it should be square root of 7 because it's u plus some constant c. Now we could probably reduce that a little bit if we wanted to, but we're not real interested in that at this point. Okay. And we probably should modify that one. Let's go multiply by square root of 7 over 7. Square root of 7 over 7 arctangent cosine of x, and then times the square root of 7 all over 7 plus c. I like that better. Okay, we'll move on. Not too bad. All right, looking at number 26. In number 26, they give you this expression here. So this one's a definite integral, so they go from 0 to 1. And they want us to do, let's see here, 26, 1 over the square root of 4 minus x squared. So again, we're going to go check and see which one does that most look like. Well, to me, most looks like this one. I have a square and a square, and then I have something there that we'll have to deal with. So if I look at it, I'm going to let my a squared equal 4, then a will equal 2, and then I'm going to let my u squared equal x squared, and then my u will equal x, and then du will just equal 1 dx, or dx. Get rid of that. We don't care if I've been blocked or something. All right. So there's dx there, don't forget. So this, I don't have to worry about my du. Du and dx are straightforward. And so now it's just a matter of using the form right here. It's just the arc sine of u over a plus the constant c. So I've got the arc sine of, let's see here, it was u, which is x over 2. And we don't have a constant, since it's a definite integral, we're not going to have a constant there. We're just going to evaluate from 1 to 0. So it'll be the arc sine of 1/2 minus the arc sine of 0. So remember that arc sine, and this is a what do I want to call it? A property of arcsine. Arcsine is on the unit circle only goes from negative pi over 2 to pi over 2. That's just a property of arcsine that we learned in pre-calculus and algebra 2 and geometry. So just keep note of that. And so the only place on the entire valid domain of arcsine where I would get a half would be right here, my 1/2. So we're looking for the angle measure that's going to make that. And if you remember your unit circle, the arcsine of a half, the only value that's going to give you a y value of a half is if you have an angle of pi over 6. And it says the arcsine is 0, so I get a y of 0 right there at 1, 0. And that has an angle of 0, so this will be just 0. So I get pi over 6 is my final solution. That's the definite integral of that particular length. Now, the last thing I want to talk about is completing the square. And we talked about completing the square in Algebra 2 and also in pre-calculus. This one we're going to do on one side. If you look at a lot of these, you have either the difference of two squares or the sum of two squares or the difference of two squares. So completing the square, we're going to try and get two squares on the same side. So here's what we're going to do. Hopefully this value is 1. If it's not, whatever's in front of here, divide everything by that value. And then we're going to rewrite it so that I have a little space to complete the square. Now, if you remember from way back, you're going to add half of b squared. Remember, ax squared plus bx plus c. All right, so we're going to add it, and then we are also subtract 1/2 b squared. So since we can't exchange this expression, we have to have the same expression. What we're going to do is we're going to add and subtract the same amount, and then we have had a net change of 0, and the additive identity is what we're looking for here. So half of 4 is 2, so I'm going to add 2 squared, and then I'm also going to subtract 2 squared. Now the reason I did that is because that makes this thing a perfect square. It makes it the perfect square binomial x plus 2 quantity squared. And then 13 minus 2 is just 9. So now this is a squared, and this, let's do it right this. This is a squared, and this one is a squared. So I have my two values that I'm looking for. Now, number 40, and I'm going to use the same, it's basically the same numerical values, but they want the definite integral from -2 to 2 of, let's see here, let's get it right, got my dx on top all over x squared plus 4x plus 13. Okay, so, excuse me, using what I got from the one above it, I'm just going to skip over that step there, and I'm going to replace this expression with that one, and I'm going to rewrite it so that the constant is first. So I've got my dx, I've got my 9 plus the quantity x plus 2 squared. So now when I go and I look at that, again, it looks very much like this arctangent expression. So let's bring this back down. My a squared is going to be 9. That makes my a 3. My u squared is going to be the quantity x plus 2 squared. So u is just x plus 2. And then du is just going to equal dx. So I have nothing to transition here. So I still have my -2. My +2 is the upper and lower bound. So writing my final here, it'll be 1/3 arc tangent of, let's see here, it's x plus 2/3. And since it's a definite integral, there's no constant that we have to worry about, so we're evaluating from 2 to -2. And so when I plug this in, I'll get 1/3 arc tangent of 4/3. And then from that, I'm going to subtract 1/3 arc tangent of, and when I plug in the -2 plus 2 would be 0/3. And let's see here. Arc tangent, remember, is, or tangent is sine, do it right, McColley. Arc tangent theta is equal to sine theta over cosine theta. So the only place where the arctangent is going to be 0, and again, arctangent is only valid from -pi/2 to pi/2. So the only place where this is going to be true is at 1, 0, where I would get 0, 1. So the angle measure that makes this thing a 0 is 0. That should be a third. And then this thing doesn't reduce anymore. And so that cancels. And our final answer is 1/3 arc tangent of 4/3. And since that's not on the unit circle, I can't simplify that anymore. And we're just going to leave it like that. Call it a day. All right there, folks. 16 minutes, the end. And as always, if you have any questions or you think I made an arithmetic error somewhere in there, please leave a comment in the section below. Have a good day. Goodbye.